So we will change this now. Okay. Okay. So we were talking about the MRR versus frequency and amplitude just now. So basically, in general rule, if the frequency increases, then basically MRR going to increase. Same goes for the amplitude. So it makes sense. Because the frequency is basically how many times per seconds the grid will be in contact with the will be indenting the workpiece material. So the more the more number of hit of indentations, then basically the number of material being removed is going to be higher. So MR should be higher. Same goes for the amplitude. So this will determine the deeper, how deep the indentation is going to be made. The deeper the indentations, the more material is going to be removed. So because of that, as amplitude increase, then the MRR also increase. Okay. This is talking about the MRR versus the abrasive diameter and concentrations. So MRR should also rise proportionately with the mean grain diameter D. When D becomes too large, then the crushing tendency increases. So what it says is this. So in theory, as MRR increase, right, D should increase, but actually it can actually decrease. It can actually decrease. This is because of this. So when D is a grain diameter, so let me just sketch this. So this is tools. Okay, this is workpiece material. So this is, let's say for example, this is a grid. Okay, let's say this is a grid, right? So this particular tools is oscillating up and down, right? So this will also it will go down from that position to this position, right? So from this position to this position, and it will go up again, right? So this is the H. This is the H, right? So as this indentation happen, right? MRR should rise proportionally. When D become too large, the crushing tendency increases. So what it says is this. So as this as this thing make indentations, the stroke maximum stroke will be the same H, right? So as the maximum stroke will be the same H, the bigger the grid going, if the grid going to be bigger, it will stroke the same amount, right? So the indentations, the maximum indentations that going to be happening beyond certain diameter will be the same, right? So for example, so whatever the depth here, the indentation depth, the maximum indentation depth will be that particular H. You cannot go any more than H. Even if the grid is bigger, then it will indent that H one, because that's how much the amplitude of oscillation going to be. That's one thing. When D become too large, the crushing tendency increase. So it says that when the D become too huge, then the crushing tendency be increased on the grid itself. So the grid itself can be broken apart. When it becomes too big, then it can be broken apart. And another thing, basically, if you look at this particular curve, in actual case, right? So if the grid become too big to beyond certain amount, then actually the MRR can goes down. The reason being is this: if the grid is become too big, then it will somehow affecting the flow of a slurry in between here. So if the flow of slurry is going to be affected, and the what do you call it, the grid is being crushed, all right? So basically, the materials, the replacement of the grid will be affected. So because of that, there'll be some blockage, some semi blockage of materials, harder for the slurry material to move through this particular gap. Okay? So because of that, then MRR will suffer. Material removal rate will suffer. So that's why because of that, then you're going to have this kind of effect. In theory, it should go up, but in actual case, it's going to dip down because of that. Because the crushing of the grid, the tendency of the crushing of the grid, and basically the blockage of that particular gap, so that it prevents a smooth flowing of slurry material between the tools and workpiece. Okay? Concentrations of the abrasive directly control number of grains producing impact. So MR is proportional to C over 1/4. So C rise to 30%. MR increase is not very fast. So what it says is this. So MRR is proportional to concentrations, but concentration over 4. So as C rise more than 30%, so if the concentration is going above the 30%, then the effect of the concentration will be plateau. Because once you have too much, if the concentrations of abrasive inside the slurry is too high, then basically it will impinge the fluid flowing through that particular gap. So because of that, then basically MRR is not going to be increased continuously, but up to maybe about 30% of concentration. Okay. Any questions? Okay. Uh, MRR versus feed force. So MRR increases with the increasing feed force, but after certain critical feed force, it decreases because abrasive grain got crushed under the heavy load. Again, as mentioned just now, uh, so you're talking about feed force. Just now I mentioned there are two force. There's a static force actually on the so there's a static feed. There's a static on top here. There is a static force that's actually pushing the tools down. So as the tool engage with the abrasive and this, there is a force, certain force actually pushing it down. So we are talking about that force. So it says here, MRPC with MRR should increase with, in theory, should increase proportionally, almost proportionally with the feed force. But after a certain critical feed force, it decreased. The MRR will decrease because the abrasive grains got crushed under heavy loads. So because if the force is too high, then even the hard particles uh, inside the abrasive, inside the slurry, will get disintegrated. Right? So, let's see. So will the slurry be recycled back to the machines or will be disposed after use? So basically what's going to happen is the slurry once will be recycled, but there is a preventive maintenance. So based on historical analysis, so on and so forth, then the operator should know how long can you use the slurry, how long can you recycle the slurry. Right? Even recycling the slurry, you have to make sure that uh, uh, there's a way for you to filter the filtering of the what do you call it, of the chipping of the chip. that being from the material being removed, right? So to a certain extent, it can be recycled, but there's some limit in terms of how much, how long can you recycle it. Okay. Any other questions? Right. Okay. Okay. So this is the component of the ultrasonic system. So you have a power supply. So this power supply usually is in the form of so this power supply is sine wave, is AC current at certain wavelength, so on and so forth. Right? So you have a transducer. So this transducer is the one that actually will generate the what do you call it, the amplitude of movement and also the frequency itself. So based on the power supply, then you're going to have amplitude and the frequency of movement going up and down. Right? That's a transducer. This is a mechanical amplifier, or sometimes they call it transformer, or sometimes they call it horn. So, right. Sometimes they call it also horn. Right? So this transformer or horn or amplifier is to amplify the amplitude of the transducer. So let's say, for example, the transducer move up and down by let's say, for example, 5 microns, then basically this transformer or horn is a mechanical device that will amplify this amplitude from 5 microns to maybe 15 microns, right? So the amplifications of that amplitude is done by a transformer, horn, or mechanical amplifier. And then you have a tools over here. So this is tool holder. This is a tool, and this is workpiece materials. So this is abrasive slurry. So there's a pump here, so you can recycle and filtering it for up to a certain amount, and then you have to discard it, right? So basically this nozzle will pump the slurry up to the workpiece, and it will be directly in between the uh, tools and also the workpiece. We're going to go through in details on this particular uh, component. So the power supply, so power supply is sine wave generator used as a power supply. Uh, Basically, the reason is you need to generate a waves uh, with the speakers or wave drivers. So you need to generate a wave. So usually power supply is a sine wave generator. It allows both frequency and amplitude to be varied. So sine wave generator, you can vary the amplitude and also the frequency and also the amplitude. So you can vary the frequency and amplitude. Just now we mentioned, so you're talking about you need to vary the frequency also the amplitude. This is kHz. It's not hertz. It's kHz. Uh, Frequency and power. This frequency and power of generate signal are controlled by the operator, so you can actually change the frequency and power signal. It convert low frequency to high frequency 10 to 15 kilohertz power. uh, Supply to the transducer for conversion into mechanical motion. So this is the power supply in sine wave form. You can control both the amplitude and the frequency, and this particular power is going to be translated into mechanical motions by the transducer. So transducer is a device that converts variations in a physical quantity such as pressure or rise and so forth. So this is the general definitions of of transducer. In USM, there are two type of transducer that usually is being used. One is a magnetostriction, magneto, magnetostriction transducer. The other one is a piezoelectricity transducer. So basically, both of these transducer, the objective is actually to change from the electrical signal into the mechanical motions. Mechanical. So it can be either magnetorestrictions or piezoelectricity transducer. So the magnetorestrictions materials transducer is the principle is this. So when you place a certain materials in a sufficiently strong magnetic field, so from the power supply, you can actually generate from the electricity you can generate magnetic field. So if you put a coil, if you make a coil and let electricity going through the coil, then what you're going to produce is actually a strong magnetic field, right? So the magnetic moments of the domain rotate in the directions of the magnetic field, become parallel to it. This process to expand and contract. So because of this particular magnetic field, the material will expand or contract uh, uh, until all the domains become parallel to each other. So basically, you need to have a materials that actually responds to a strong magnetic field in terms of its dimension. So if you find this particular materials and the very common materials is called smart materials of amorphous alloy of ferrum. So this is the common materials that's being used in this magnetostriction transducer. So when these particular materials being exposed in the magnetic field, then basically it will change in its dimension. Not much, but just a bit. You're talking about just now. You're talking about 5 microns. So you're talking about very small changes in dimensions. So when you have a when you have materials, I'm simplifying it. I'm simplifying it. So this is, let's say, a coil, right? This is coil to the power supply, and this power supply is basically sine wave, right? So basically, so we have magnetic field that's going to be on and off and on and off and on and off. Due to that, then basically this particular material will actually, the dimension of this particular material will change. Will change based on the power supply. So we'll expand, go back to original, expand, go back to original, so on and so forth. So because of this, then you are transforming the electrical source into mechanical movement, right? So you can also use piezoelectric transducer such as quartz, leads, or zirconate. Basically, this particular material generate a small electrical current when compressed. Their dimensions altered when being subjected to electrostatic field. So these materials, physio transducer, actually once you compress it, it will change the electrical current. So vice versa, if you supply electrical current in it, then basically it's going to change in size. So again, this particular materials can actually transform the electrical source, electrical signal into mechanical motion. Because once because the charge is directly proportional to applied voltage. When electrical current is applied, then materials increases minutely in size. Right? When the current is removed, the material is instantly returns to its original shape. So because of that, again, the power supply is in a sine wave, right? So because of that, increase in size, and then when it goes, when the current goes to zero, then basically it will go back to its original size. And then when there's another power supply, subjected on that materials, it will expand a bit. Right? So because of that, then you actually transform the electrical currents, electrical power supply, into mechanical movement. So mechanical amplifier, again, so that you remember. So we have power supply that supply power to the transducer, right? So this is transducer. Oh, and then basically under the transducer is the my drawing. This is the amplifier. So if you look at this is the transducer. This is the amplifier. Okay? So the shape of the tool holder in a cylindrical or conical or modified cone, which helps in magnifying the tool's tip vibrations. So its function is to increase the tool vibration amplitude and to match the vibrations of the acoustic load. Therefore, it must be constructed of a material with a good acoustic properties and be highly resistant to fatigue and cracking. So these are the monel and also titanium, a good acoustic material properties are often used together with stainless steel, which is cheaper. So basically, the mechanical amplifier, the purpose of it is actually to increase the vibrations, the amplitude of the tool vibrations, to match the vibrator of the acoustic load. So basically, and usually it has three shapes. You can make this amplifier or horn in three kind of shapes. One is exponential shape like this, taper, or step. This is the most efficient in terms of amplifying the motion. However, is much harder to make this shape compared to taper and step. Right? So again, this power supply transducer here. This will have a very minute motions. So this transducer will amplify the transducer motions into a bigger amplitude. Okay. Any questions?
Haris ada soalan je dekat chat.
Okay.
Dah jawab Zee, dah jawab.
Oh, dah jawab.
Okay. Tools. So we talked about just now. We talked about power supply. We talked about the transducer, and we talked about the amplifier or the horn. So this is a tool. Tool materials should be tough and ductile. So tool material must be tough and ductile. So remember, tough doesn't mean hard. Toughness measured when you want to measure toughness, you use the Chappie impact test, not the hardness test, Beaker hardness test, right? So material should be tough and ductile. Low carbon steel and stainless steels give a good performance usually for this particular for the tool materials. So remember, the workpiece material must be brittle, but the tool material must be tough and ductile. Usually it's 25 millimeter long. Usually, its size equals to the whole size minus twice the size of the abrasives. So when you want to design the tools, you want to design it such that the size of the opening so if this is your tools, if this is your tools, uh, if this is your tools, so if you want if you want to make a hole of that size, right? If you want to make a hole this size, so this hole size, they say this is diameter, so this will be diameter plus 2 the abrasive grid size. Because when these tools goes in here, when these tools goes and make a hole, there must be a gap on the side, and this gap usually is a gap of 2 grid size, 2 grid size. So when you make distillery, you can make a distillery with a grid, and basically you can purchase a grid of particular mean diameter dimensions. So when you want to design a hole, design the tools to make hole of the size that you want, you have to make sure that you take into considerations on the side clearance. Okay? So the size equals to the hole size minus twice the size of the abrasive. Mass of the tool should be minimum possible so that it does not absorb the ultrasonic energy. So these tools, if the I mean you want to make sure that the mass of the tool, so inside it, it can be you can make a hollow inside, so on and so forth, so that the mass of the tool is not too high. If the mass of the tool is too high, then basically, remember, the energy is being transferred up here from the transducer. Transducer goes to the horn or the amplifier to the tools, right? So this if you have a solid material in here, then it will somehow absorb the ultrasonic energy, and it cannot be transferred down to the grid and make indentation on the workpiece, right? So you have to, the mass of the tool should be as minimum as possible. Uh, it's important to realize that finishing or polishing and operation of the tools is important. So when the surface of the tools itself, uh, the the image of the tools itself will be transferred to the workpiece. So if you want to have very fine surface finish, then you need to polish it. So that's why it's here. It says that it's important to realize that finishing or polishing operation on the tools are sometimes necessary because surface finish will be reproduced on the workpiece. So this is same as when we talk about electrochemical machining, when we talk about EDM process, same concern is need to be considered. Tools and tool holder are often attached by silver bracing. So usually you brace between tools and the tool holder or the horn on the top. Okay. Okay. Abrasive slurry. Abrasive slurry contains a fine abrasive, usually ranging from 15 microns to 150 microns. So it's very fine. So we used to microchip erode the material. So I explained this just now. Uh, so the slurry is pumped through a nozzle close to workpiece. So you have to is a direct flow between the fluid and the workpiece cap. So you're talking about a rate of 25 milliliters per minute. So this is quite high flow rate that need to be achieved. So these are some common type of abrasive. So it must be all these materials are basically very, very hot materials. And you can use this liquid as a fluid. And most often than not, we use water for this particular case. This is basically process parameters. So this is a chipping rate, this material removal rate. So what affect material removal rate? Accuracy, surface quality, so on and so forth. Machining, stiffness, rigidity, workpiece, ductility, hardness, so on and so forth, abrasive slurry, tools, and work conditions. So all these can affect chipping rate, MRR, and also can affect surface quality and also accuracy. Yeah. Advantages of USM process. Basically, you can machine any material regardless whether it's conductive or non-conductive. But the condition is basically it must be brittle. Material must be brittle. USM apply to USM apply to machining semiconductor of such as silicon, germanium. So for semiconductor wafer, so wafer for the semiconductor is made of silicon, germanium, so on and so forth. And this is very, very hard and brittle materials. So USM is being used to machine semiconductor materials. Suitable for precise machining brittle materials. It does not produce electrical, thermal, chemical abnormal surface. So just now the questions whether it's actually generate heat ataupun tidak. Basically, it produce it, but it does not. It's not significant, such that it does not have any impact on the surface of the workpiece. USM also can actually be used to drill circular or non-circular hole in a very hard material. So you can do USM drilling. We're going to, I think there are a few slides of this that talk about that. Less stress because of this non-thermal characteristic. So there's no thermal stress developed using this particular process. And machine parts of USM possess a better surface finish and higher structural integrity because there is no heat or thermal stress involved in this particular process. Disadvantages, low MRR. So compared to other process, is maybe on the low side. Second is hard to drill deep as a slurry movement is restricted. So you cannot drill or machine something too deep, because as you go deeper, then basically the slurry movement will be problematic, and the material removal is being done due to the impact between the grid, which is inside the slurry, and the workpiece and the tools. So if the slurry cannot move, then you won't be able to machine. Okay. Wear rate is high due to abrasive particles. So the tool wear is high due to abrasive particle mentioned just now during the indentations. Both the workpiece and the tools will be indented, but the workpiece will not be the material of the on the tool will not be removed because it's ductile. It will deform. It will deform. So, but again, compared to other processes, tool wear rate is considerably high. Tools made from brass, tungsten carbide, MS tools, and so forth, will wear with from the actions with abrasive grid with a ratio range from 1:1 to 200 to 1. So you can, depending on the material that you use as a tool, the wear rate, the ratio can range from 1:1 to 200 to 1. Okay. And USM can be used only when the hardness of the workpiece is more than 45 HRC. So as mentioned just now, it must be brittle. The workpiece must be brittle. So basically, effectively, it can actually start to do the impact fracture on the workpiece material if the workpiece material hardness is more than 45 HRC. So that's some of the disadvantage of the USM. Application, machining cavities, electrical and mechanical, used to machine fragile component in which otherwise scrap rate is high. So used to machine fragile component in which otherwise scrap rate is high. So if you have a fragile component, uh, then basically you can use this particular process, because the material removed using this particular process is a very minute. So you're talking about the grid size about 15 microns. So indentations may be much less than that. Maybe the indentation itself maybe around maybe 3 microns. So because of that, then basically the mechanical force impart on the on the workpiece per cut is very low. Used in multi-step process fabricating silicon nitride, turbine blades, machining hard brittle metalloys, semiconductor, used to machine round. So it can be used for machining round, square, or irregular shaped holes and surface impressions. Used in machine dies or whatever. Okay, so these are basically the application of USM, self-explanatory. So again, if this particular session's expired, please log into the next session. Example of USM. So you can do actually rotary USM process. So mentioned just now, the tools normally will move up and down only, right? But it can also move up and down and turn around and rotates at the same time. So if you have tools as such and can do rotations, then you can do coring using this particular process, right? So coring means that you can cut off uh, the the center of it, or you can do drilling. So again, using the same operations, that you can do a drilling or coring by rotary USM process. Some other examples of USM that can be used is basically, so this is a regular ultrasonic sinking. This is just like EDM process. So it's vibrating up and down. So it transfers the image on the tool to the workpiece. Or you can do actually, so for this particular tools, basically you have to make sure that you machine these tools properly to the exact replica of a finished good that you want, right? So it costs some money to do the machining. Or you can actually have a very simple tools like so, and we have a precise control, NC control on the tools that can move X, Y, and Z directions. So